Section 8.8, Improper Integrals. First off, let's begin by talking about the difference between a proper and an improper integral. Now, a proper integral is the kind we've been always using up till now in calculus. So the obvious situation is that the numbers that we're using for the limits of integration are finite values, and of course, f is a continuous function on that interval. When those things are not true, we have what are called improper integrals. So anytime the limits of integration, right, maybe become infinite, for instance, if we're going like from 1 to infinity, or if there are some discontinuities on the interval, so in this example, as you can see clearly, there's a discontinuity here at 0, right? When those problems exist, those become improper integrals. Now, we can still figure out what they are, but we need to adjust how we apply the fundamental theorem of calculus. So to begin, let's assume we have a situation where we have our limits of integration with one of them being infinite, okay? So we want to find the area, if you will, from 0, or I should say from some value a to infinity. So in this case, what we have to do is kind of rethink how we do the fundamental theorem of calculus. So we'll compute the antiderivative as normal, but once we figure out what that's going to be, we're going to go ahead and let that value, and we're going to place a variable there, if you will, and explore what happens as it becomes infinitely big. So to give us things to work with, we're going to replace our infinity with a letter. I like to use b if it's the upper limit, and then do the work. And when we do the fundamental theorem of calculus, we'll plug a in, we'll plug the b in, and then when we have that final expression in terms of b, we'll evaluate the limit. And that will tell us how that antiderivative behaves as this value becomes infinitely big. Now, on the other side of it, what would you do if you had an integral with a bottom number was going to negative infinity, right? Well, we'll do the same thing. We'll find the antiderivative, we'll do the fundamental theorem of calculus, but we're going to replace this infinity here, this negative infinity, with some a. Okay, I like to use a for the lower limit of integration. And then after we find our antiderivative, we'll plug in the number b, we'll plug in our a, and then we'll evaluate that expression of a as it becomes going to negative infinity, right? As it becomes infinitely small. And again, that will tell us the value of it as those limits of integration, started out where they were. Now, the only other interesting place is, what if you had infinity in both places, right? You're going from negative infinity to positive infinity. Well, in this case, what we have to do is break up the integral. So we select some number, right? An easy number, 0, 1, something that's easy to work with, obviously, and we break up into two integrals. So we'll figure out what's going on from negative infinity up to that number, and then a number up to infinity. And we do that because we're trying to create a situation where we're either using option A here or option B, where we only have infinity in one spot. So you basically treat this part of it, right, just like we did here in option 2, and then the second part of it here, just like in option 1. So now we're going to do the limit, obviously, of the antiderivative here with this being some unknown a going to a negative infinity, and then the limit as some unknown b here goes to infinity with this antiderivative. So the situation we have two infinities really uses one of each to figure out the answer. Now, one quick note. In general, obviously, if we come to an answer, that's our solution. And because we came to a solution, we refer to that as it converges to an answer, since obviously we're going to infinities. Now, obviously, there will be some situations when we evaluate the limits that do go to infinity. In those cases, they don't actually have an answer because, again, it's just an infinity, and we refer to those as diverging. So let's try our first example. So here we're going to go from 1 to infinity of the integral of 6 over x to the 4th. Now, the first thing, obviously, is finding the antiderivative. And this is going to be no different than what we would normally do in any given problem. So what I'm going to do before I worry about doing the limits and stuff is just figure out what this is going to be, okay? So this right here is basically negative 2 over x raised to the, over x to the 3rd. If I erase that, make it look a little nicer. Plus c, okay? So just figure out the antiderivative by whatever means necessary. Here, of course, it was just power rule. Now, once you do that, now we can adjust how we actually do the fundamental theorem of calculus. So what we're going to do is we're going to find the limit as some unknown b goes to infinity. I like to use the letter b whenever I use an upper limit here, okay? And of course, that means it's going to be on the antiderivative here. And we're going from 1 to that b. Okay, so we're definitely still doing the fundamental theorem of calculus, but we're just replacing the infinity with a b, just so we have something to work with. And once I, plug in the top and plug in the bottom and subtract them, actually do the fundamental theorem of calculus, then with that result, we can apply the limit. So by fundamental theorem of calculus, okay, the limit we're going to be working with here is plugging in the b. So that would be negative 2 over b to the third. And then if I plug in 1, that just gives me negative 2. Or I should say plus 2, because I'm subtracting a negative 2. Okay, so again, plug in the b, plug in the 1, subtract them, it works like this. And now that we've worked out the fundamental theorem of calculus, we have the extra step of now evaluating the behavior of this result as b becomes infinitely big. Now, clearly letting this denominator go to infinity makes it work out to be 0. So what we can say about this improper integral is it converges to 2. Now, in this example, we can see that the lower limit of integration is in infinity. So in this case, obviously going to negative infinity because it's on that side. So in this case, we're going to replace this with an a. And then as we do the fundamental theorem of calculus, we'll evaluate the behavior as that a becomes negative infinity. So first off, let's remind ourselves what the antiderivative is. Because it is just x squared plus 1, that should be pretty obvious that it's arctangent. So that'll be easy. All right, so let's convert this. So we're going to look at this as the limit, as our lower limit a approaches negative infinity. Okay, the antiderivative, of course, being the arctangent of x, and we're going to go from a to 0. So when we apply the fundamental theorem of calculus, we'll go ahead and plug in 0. Now the arctangent of 0, of course, is asking where is tangent equal to 0, which is 0, minus, and in this case, just the arctangent of the value a. So let's evaluate the limit. Now, of course, 0 will remain constant, minus. So we're asking ourselves, what happens to the value of arctangent as a becomes negative infinity? Okay, so what that means, and maybe helps to think about the unit circle on this. Okay, remember 0 here is where, arctangent is going to equal 0. If we went this direction, the values of sine, are getting bigger and bigger, and the values of cosine in its denominator are approaching 0. That creates a vertical asymptote. So this way, since you're taking the values of sine and you're dividing them by smaller and smaller and smaller numbers, the value overall becomes infinitely big. The same is true if we go the other way. So here, as we go down, the only difference is the values of sine are positive. So obviously, as we get closer and closer down this direction, the values of cosine, again, are approaching 0. So this time we have a negative value that's being essentially multiplied by larger and larger numbers as you divide by smaller ones, and therefore it approaches negative infinity. So when we ask ourselves what happens or where is arctangent approaching negative infinity, it's going this direction, and it's approaching negative pi over 2. So obviously when you take 0 minus negative pi over 2, we can say it converges to the value pi over 2. Now let's look at an example where we obviously have infinity with both the top and the bottom. Now first off, obviously we want to find the antiderivative. Now here, I think a really easy way to find this antiderivative would just be letting u equal e to the x. And by substitution, we would clearly get an arctangent. So this is going to be the arctangent of e to the x. All right, so let's work on this. We're going to make this, we got to break it up, I should say. So what we're going to do is, first off, I'm going to rewrite this as the integral of some a up to some easy number. So I want to use something, easy like 0. So we'll do that. And then since I stopped that one at 0, then we'll pick up our next part at 0 and go to some b. Okay, so I'm going to break this up this way because that way I can tackle each infinity separately. Now, the nice thing is, of course, both of these have the same antiderivative, so it's just the limit part that's going to be a little bit different, okay? So what we're going to do is we're going to do the limit as a approaches negative infinity, right, of our antiderivative. So in this case, the arctangent of e to the x. Okay, that's going to go from a to 0. And then we'll add on to that the limit. Now with this one, we're going to have b go to positive infinity. And that's going to be, of course, on the arctangent of e to the x with our limits of integration being, 0 to b. So when we actually plug it in with fundamental theorem, the limit as a goes to negative infinity is going to be working on, if you plug 0 in, that's just a 1. And the arctangent of 1, of course, is asking you, where is tangent equal to 1? So that's just pi over 4. And then we'll subtract from that the arctangent of, plugging a in, and that's simply the arctangent of, e raised to the a. And then we'll add on the same thing over here. So now b is going to positive infinity. Plugging in a b is just arctangent of e to the b. And then, of course, plugging 0 is the same thing. It'll be that pi over 4. All right, so now we got to think about where these limits go. Now, obviously, we have some constants, so it's just this part of it. So our final result is going to work out to be First off, this part here goes to, of course, to pi over 4 because it's constant. So looking at this part, as we let a become, approach negative infinity, that takes it as e to the negative infinity, which goes to 0. And the arctangent of 0 is just asking you, what value of tangent makes 0, and that is 0. Plus, and we basically get the same thing over here. Now the difference though is, this time when I plug infinity in, it's e to the positive infinity. So in this case, what's going to happen is we're looking for where is the tangent becoming infinitely big. Well, that's going to happen at pi over 2, because that's obviously when the denominator of tangent, which is cosine, is approaching 0. So to that end, this is going to be a pi over 2. That's when tangent becomes infinitely big. And of course, the constant pi over 4 is right there. So if I combine all those pieces together, that equals pi over 2. So in this case, the improper integral converges to pi over 2. Now let's look at the other situation. So instead of having maybe our limits of integration be infinite, now we have discontinuities we have to deal with. So if there's a discontinuity, obviously, where the endpoint here, like b, is the problem, okay, I'm just going to replace it, and I like to just use some other letter, for instance, c, if you will. But we'll just replace it, actually I take it back. I like to use a b if I'm the upper limit, but we'll replace it with a letter and then basically say, well, let's do the antiderivative and evaluate what happens to that answer as, this letter goes to the number I'm not able to plug in. Because obviously this problem is giving, this number up here is the problem. So we're going to figure out the limit as it goes to that. Now, if the lower number is a problem, okay, so the lower limit of integration when you plug it in is some sort of discontinuity, again, we'll replace it with a variable, find the antiderivative, and then after doing the fundamental theorem of calculus, we'll look at the behavior as that variable becomes that number, okay? And what I want to say, as you can see these here, is when you're dealing with the upper number, okay, that means you must be approaching from the left, okay? And that's important to understand because obviously we're within an interval here, so if we're approaching the upper limit of integration, we have to come from the left side. Down here, if we're kind of replacing this lower limit, obviously we must do a one-side limit from the right. Because again, we're bounded by this interval, so when we do the limit, we're coming from this side to see where that's going. Now, should there be the situation where there is a problem, some discontinuity, but it's somewhere in between the limits of integration, you basically do the same thing we did before where we had limits of integration both being infinite. We're going to figure out where that number is, right, and break up the integral at that value. And then for each one of these, we use each option, okay, where one of them has a problem on top and one on bottom, and you just do each one of these separately. So let's look at our first problem. And again, just to begin, let's quickly do the antiderivative. So the antiderivative of 10 over x with respect to x is obviously going to be the 10 times the natural log of the absolute value of x plus c. Okay, that's an easy one. So let's reframe our issue. So looking at the limits of integration, 5 is okay, but clearly you cannot plug 0 in. That's a discontinuity, right? So what we're going to do is we're going to reframe this to say that we're doing the limit as a, and again, since it's a lower number, I like to use a, is approaching 0 from the right. Because obviously, if you want to go to the lower limit of integration, you're coming from the right side. And that's going to be on, obviously, the antiderivative. Okay, and we're going to be evaluating that from sum a to 5. Okay, so just like before, we replace the problem with the letter, and now we'll do the fundamental theorem of calculus and evaluate the limit. Okay, so we're doing the limit here as a approaches 0 from the right. By fundamental theorem of calculus, this is going to be 10 times the natural log of 5 minus 10 times the natural log of the absolute value of a. So when I work out the limit, obviously this remains constant, so we got 10 natural log of 5. And so now that we look in this part, if we let a approach 0 from the right, that means when you think about the graph of the natural logarithm, right, which looks like this, as we approach 0 from this side, we're approaching negative infinity. So we're basically subtracting negative infinity, and clearly when you take a constant and essentially add infinity, that just becomes infinitely big. So in this case, the answer is it diverges and it just becomes increasingly large. Now let's look at a different situation. So clearly 0 in this case is okay to plug in, but 8 is not. Okay, plugging in the upper limit of integration does result in a discontinuity here. We're divided by 0. So again, we're going to find the antiderivative, and we're going to replace the top number and do the limit there. Now, we're going to have to quickly figure out what this is going to be. And with this situation, I think the easiest way to tackle it would be just to do some u substitution. So when we're doing this, I would say the u would probably be just this part right here. And then you can just adjust and find your antiderivative. And what happens is it'll work out to be -6 times the square root of 8 minus x plus c. Okay, so I did skip the steps, but this was just basic u substitution, choosing 8 minus x as my u. So now let's adjust. We're going to be doing the limit as a b value. I like to use b for upper, right? Approaches 8 from the left, because again, that's the upper limit. The antiderivative is negative 6 times the square root of 8 minus x. And we're going to go from 0 to some b. Okay, so let's go ahead and apply the fundamental theorem of calculus. Okay, so the limit remains the same. So plugging in b is going to give me negative 6 times the square root of 8 minus b. And then we're going to subtract a negative, so we'll just make this a plus, and that's going to be 6 times 8, square root of 8, right, when you plug 0 in. And so doing the limit, we're going to ask ourselves what happens, right, as we plug in, 8 from the right in here, and that just zeroes this out. So that's basically just gone. So the whole thing really just works out to go to 6 square root of 8, since obviously this part goes to 0 and this remains constant. So in this case, it does converge to this value. Now in this situation, when you first look at it, you might say to yourself, well, there's no problem with these numbers, and that's true. Negative 1 and 2 can both easily be plugged in without issue. Now the thing we need to talk about though is that you should immediately recognize there is a number that can't be plugged in, and it's 0. And the issue is 0 does lie between negative 1 and 2. So even though it's not a limit of integration, the issue that we're coming to is, obviously found inside in the middle, and so we're going to break it up and do 2 separate limits. Now, of course, both those limits will share an antiderivative. So again, real quick, let's just calculate what that's going to be so we can work with it. And of course, by power rule, the antiderivative here is just going to be negative 1 over 2x squared, okay? So we're going to use that as we plug stuff in. All right, so let's break this up. So we want to first off figure out where that number is, and it's 0. So what we're going to do is we're going to basically break it up into the integral from negative 1 to 0, and then add the other integral from 0 to 2, okay? And obviously these are the issues, all right? So to do that, we're going to do the limit, our first one, and that's going to be where we approach b, okay? I should say b goes to 0, the number is a problem, okay, from the left. The antiderivative is negative 1 over 2x squared, okay? We're going to go from negative 1 to b. Then we're going to do the limit where a is approaching 0 from the right, because this time it's the bottom number that's the problem, okay, of our antiderivative. And this is going to go from some a to 2. Okay, so let's go ahead and do the fundamental theorem of calculus. So with this limit, as b goes to 0 from the left side, plugging in b obviously is going to give us negative 1 over 2b squared. Plugging in a negative 1 really just makes it just a 2 on the bottom. So really it's just subtracting the 1/2. So when we do that, that just basically becomes plus 1/2. And then the next limit, and in this case, as we plug a 2 in there, that's going to basically make this negative 1/8. And then again, plus 1 over 2a squared, because we will be subtracting the negative. So as we plug in 0 here, both sides of this thing are definitely going to go to negative infinity. So that's going to go to negative infinity plus 1/2. And then over here, we do have that negative 1/8. But again, 0 from the right here is actually taking us to some positive infinity. Now, overall, we are looking at this as we're adding them together, but technically these two limits came from two different improper integrals, and so we're not going to worry ourselves with putting these pieces together, but instead focus on the fact that this part right here from the first integral here that was technically improper, this diverges, okay? It does not go to a number. Likewise, when we look at this part of it, right, that came from the second integral, which again by itself was an improper integral, which also diverges. Now, when you have the situation where you're breaking it up into two improper integrals, if they both are diverging, the overall result is to say that all of this diverges. Now, with this last example, I don't want to fully work it out. I just want to talk about how we would tackle something like this. So in this situation, we definitely have two different things that are kind of an issue. It's kind of a mixture, right? So we have obviously an upper limit of integration that's infinite. That's an issue. But our lower limit of integration also is a problem because it's a discontinuity. You can't plug 0 in. So while I'm not going to work it out, the approach is that you would break this up into two separate situations, where one of them is going to be dealing with our discontinuity, and the other one's going to be dealing with our infinite limit of integration. So obviously, to break this up, we want to choose some value. And I would just choose an easy number like 1 to do that. So we can go ahead and go from 0 to 1, and then go from 1 to infinity. So that way, what you can do with this integral, right, the first one is basically do the situation where you can find the antiderivative, do the fundamental theorem of calculus, and let this lower limit be some a, and you'll just evaluate the behavior as a approaches 0 from the right. Up here, same antiderivative, but this time you'll be replacing this with some b, and you'll be evaluating that result as b becomes infinitely big. So this kind of is a mixture of the two different situations we looked at, where we have an upper limit that's infinite, and then obviously a discontinuity on the lower limit.